Periodic table is a simple arrangement of elements, systematic arrangement of elements. Many times the students think that periodic table happens to be a chapter, but no. Periodic table is not a chapter. Periodic table in fact is a tool to understand chemistry. Periodic table is just a way to make the study of chemistry more systematic. Nothing more than that. Okay. There has been a lot of attempts to arrange the elements in some systematic order. Lot many scientists tried it. The earliest attempts were made by some people, like early people, very early people that we talk about. Then the early Indians, the early Greeks, the early people, they classified the elements in total 5 elements. जिसे हिंदी में कहा जाता है पंच तत्व और पंच महाभूत. Classification of everything into just 5 elements were not enough for our understanding. We had to have a little bit more understanding that how much we know about it. How can I consider all the solids to be same? I just can't keep one name for everything which is solid. So that is why a bit more of classification was required. Another classification that they tried to do was, let us classify the substances as metals and non-metals. एक बात ध्यान रखना, पूरे periodic table में whatever the elements that we have actually just 2 liquids. One of the liquid happens to be mercury and bromine. These are the only 2 liquids that we have in periodic table. You may say a liquid has cesium. Certain people say cesium is a liquid, certain people say gallium is a liquid. But be very clear, when we talk about the normal temperature, when we talk about the room temperature, the temperature is 25 degrees Celsius, that is 298 Kelvin. Cesium has a melting point of something like 29 degrees Celsius and gallium has 37 degrees Celsius. So at 25 degrees Celsius, cesium as well as gallium would be solids. So periodic table has maximum solids, the few are gases and only 2 are liquids. Is that clear? So that happens to be the entire elements that we have. So when we talk about the classification in the case of metals and non-metals was a bit vague. And there are certain substances which can't be classified as metals or non-metals because they have the properties of both. So again it became a bit difficult to classify as metals and non-metals. Then they further tried to classify them in terms of chemical properties. Many of the elements were unknown at that time. So whatever elements they knew of, they tried to arrange them into certain arrangements. Now the very first arrangement that was tried was by Dobrinier. He talked about the triads. The Dobrinier triads. What Dobrinier did was he made the groups of 3 of certain elements. And he tried to give them the name of the families. There were groups of 3s. Now these groups of 3s could be something like, we have the chlorine, bromine, iodine. Okay? Or maybe calcium, strontium, barium, then oxygen, sulfur, selenium, lithium, sodium, potassium. Now these groups, they were having similar chemical properties, and apart from having similar chemical properties, they had one very peculiar property, and that was, if we added the atomic mass of these 2 elements and divided by 2, we would get the atomic mass of the 3rd element. So the atomic mass of the atom in between was the average of the atomic mass of the 2 elements. So this was a typical case that was important for the Dobrinier's triads. Like, this was called halogen. is the name given to sea salt. So it was halos generating, the sea salt generating. So it became halogens. Okay? These were called chalcogens. Ore. When we talk about metallic ores, they are majorly oxides, sulfides or selenites. So they were earth generating or ore generating. So they were called chalcogens. Then we have nitrogen, phosphorus, arsenic. When we talk about these elements, they have a peculiar characteristic that these elements, they produce poisonous gases. They are poisonous gas producers. They were called nicogens. Nicogens is not N, it's P. Pneumonia. That particular word is again poisonous. Okay, so these are poisonous gas generating, the nicogens. Okay, in the same manner, this was called alkaline earth metals. In the same manner, this is alkali metals. But this didn't work because all the elements could not be put into these three groups. Then another scientist came into being, and his name was Newland. That if the elements were arranged in the order of their atomic masses, then every eighth element had a property similar to the first. Now this he felt something like there is a divine intervention, because the 7 happens to be a very predominant feature in Earth. 7 is a very lucky 7, we call it, like 7 wonders and 7 stars, 7 seas and 7 continents and 7. So he thought that there is something against 7 working here. So he said that this is an octave. Octave doesn't contain 8, it contains 7.
Yes, sir.
8 is a repetition of the first.
Yes, sir.
Okay? So that's what he called octave. That it's similar to the music notes. It's something like the 8th element happens to be the repetition of the first, a little higher. And same is what's happening here. So he said it's octaves, the Newland law of octaves. But then, Newland thought again a peculiar problem. That he could not put all the elements in terms of these octaves. There were certain elements which were not falling in the octaves. So this work is first 20 atomic masses. Then came 2 more scientists. One person, the name was Lothair. We have Lothair and we have Bentley. Now these 2 people were contemporary. That they were working at the same time. They had different ways to get along with it. Lothair said that he would take the curve, he would take the graph, and he will plot the atomic volumes with respect to atomic masses. That was Lothair's atomic volume curves. Fine. Now it was easy to find out the atomic volumes. What he did was, he took atomic mass and he divided by. Now I believe you understand that mass by density will turn out to be volume. So that is how he got atomic volume. Okay. So he took atomic mass divided by density and it gave us atomic volume. In regards to that. So what he did was he found these things for all the known elements. And he got atomic volumes. He made a graph of atomic volume with respect to atomic mass. When he made this graph of atomic volume with atomic mass, he found that it simply turned out to be like this. And he found that all the elements which were having similar properties were occupying similar positions on these curves. Okay, so if I make a straight line like this, then all the elements falling on this straight line would be having similar properties. So that was Lothamier's curves. That was a brilliant idea, it was a brilliant thing. But then there was another person who was Mendeleev. Now Mendeleev, he was a school teacher, a chemistry school teacher. And he was trying to explain the elements to the students. Now, he wanted the students to learn the elements. And if he wanted the students to learn the elements, he wanted them to somehow make something. So what he did was, he took cards, simple cards, and he wrote every element name. जिसे हम flash card बोलते हैं आज. So he made some cardboards, small pieces, and he wrote the symbol, the name of the element, and he wrote its properties, whatever property they knew at that time. He simply took it, and he tried to arrange the elements with similar chemical properties. Be very clear, Mendeleev tried to arrange the elements with similar chemical properties. So what he did was he made certain groups and said this is the element is having this property, okay, this element. He just started putting the cards, nothing more than that. He just started arranging them. When he finished off the cards of whatever known elements were there at that time, he got certain groups of the elements having similar property. Now what he did was he started arranging the elements in their other properties, order. Like let us say he started arranging them in the order of densities, or he talked about chemical properties. No. He didn't arrange them in the order of atomic masses. He didn't. Shocking it might seem, but he didn't arrange them in the order of atomic masses. He arranged them in the order of chemical properties. And the most important chemical property that he chose was the valency. Valency, that means the combining power. How many atoms it's combining with. And that's what we have got from the darkness atomic theory. The combining power. The law of multiple proportions. The law of constant proportion. They give us combining power, the valency. So he just arranged the elements in the order of similar valencies. Okay. Now, once he had arranged them in the order of similar valencies, and then he arranged those elements within a group in some order, he was shocked to find one particular thing. And that shock was, all these elements, they turned out to be arranged in the order of atomic masses. He didn't arrange them in the order of atomic masses. He arranged them in the order of chemical properties, and that too valencies. They just turned out to be arranged in the order of atomic mass. So atomic mass is not what the thing was he was looking for. It turned out from that particular arrangement. I don't know who told us and who predicted that Mendeleev arranged them in the order of atomic masses. If you have ever seen the Mendeleev's periodic table, it has absolutely nothing to do with atomic masses. But atomic mass के तरीके से arranged ही नहीं है. Obviously what he did was, see, he had an arrangement like, you will be shocked, अगर तुम्हें ज़्यादा ही shock पड़ रहा है तो, lithium, sodium, potassium, rubidium, cesium. Do you know which elements are near to it? Placed along with them? No. Copper, silver, gold. He placed copper, silver, gold along with these elements. And this was called the first group. The second group, beryllium, magnesium, calcium, strontium, barium. And you know which element is alongside it? Zinc, cadmium, mercury. Where is the atomic mass? Where is the order of atomic mass here? The similarity is, these all elements have valency 1. These all elements have a valency 2. So he arranged the elements in the order of valencies. But yes, if you eliminate here, now this is the order of atomic masses. Now once he found that these elements, and then he gave a periodic law. The physical and chemical properties of the elements are periodic function of their atomic masses. Now this happens to be Mendeleev's periodic law. He simply said that if the elements are arranged in the order of their atomic masses, then we would find that the similar property elements will fall under each other. That's what he did. Now be very, very clear. When we talk about this arrangement, when we talk about this arrangement of elements, again, while arranging these elements, Mendeleev again emphasized the chemical properties. At many places what he did was, he actually reverted the order of the atomic masses in favor of the chemical properties. He himself did not have any faith on the periodic law, this atomic mass periodic law. This periodic law was the outcome of the table. The table was not the outcome of this law. He deduced this law from the table. But what we think is, he made the table according to it. No, he didn't. Looking at the table, he could get this rule. But now, he became so much obsessed with this law, he was so confident of this law, that many places where he found that the atomic mass order was different from the order of the valencies and the chemical properties, he actually said that you might have got the atomic masses wrong. He was so confident and he was so adamant. He said you have got the atomic masses wrong. And that's what he did. He actually corrected many of the atomic masses. And most of the places he was found to be right. किसी भी चीज की सच्चाई या उसके सही होने के तरीके को पता करने का तरीका सिर्फ यही है, put it in a situation where it is supposed to be proved wrong. It is the best way to prove something right. Now what he did was, he was making the arrangement in the order of chemical properties. Many places, such as he had boron, aluminium, and he had carbon, silicon. Okay. He had the element here, this is beryllium, magnesium, calcium. Here we have phosphorus and arsenic, nitrogen and phosphorus. Now, when he had calcium, the next element that he had after calcium in atomic mass was arsenic. So according to the order of atomic masses, arsenic should have come under aluminium. Since Mendeleev was not making the periodic table according to the atomic masses, and he was considering the chemical properties as a major consideration, he didn't put arsenic under aluminium. He didn't put arsenic even under silicon. What he did was, he placed arsenic under phosphorus. And arsenic has similar chemical properties to phosphorus. Now, the people who could not make the periodic table, who could not understand it, who were envious of what Mendeleev had done, they started making fun of him. What fun they doing? Mendeleev, your periodic law is wrong. You have left a vacant space. Now, Mendeleev was even more adamant than they had thought. He was such a stubborn fellow that he said, my periodic table is absolutely correct, my periodic law is absolutely correct. You just have not discovered these two elements as yet. There must be two elements. Here he called it Eka aluminium and he called it Eka silicon. He predicted its melting point, he predicted its boiling point, he predicted its chemical properties. They found these two elements. And when they found the property of these two elements, they were so shockingly similar to the property that Mendeleev had predicted that people now started accusing him. Beta, you had already discovered these elements. Just to show that your periodic table is right, you asked us to discover it. It was so successful. Now, the people who were blaming Mendeleev, they became the followers. Ultimately, They followed him. And what the people started doing? They started making the periodic table. Every new element that they were being discovered, they always started putting it there. They just did it. They made another table and they started looking for the gaps. They searched for the gaps. They predicted the property of the elements and then started searching for them. They followed him. And what the people started doing? They started making the periodic table. Every new element that they were being discovered, they always started putting it there. They just did it. They made another table and they started looking for the gaps. They searched for the gaps. They predicted the property of the elements and then started searching for them. And this method proved so fine that within 5 years they discovered 12 new elements. And Mendeleev had made its point. But there were still problems with the Mendeleev's periodic law. The elements didn't turn out to be in the same order as the atomic masses. But nobody could pinpoint what the flaw was. There was a flaw. Everybody knew it. Not in the table which was made according to the atomic the chemical properties. There was no flaw in the table. The flaw was in the periodic law. At that time, another whole family was discovered. And this family was called the family of the inert gases or the family of noble gases. Now, Mendeleev's periodic table had some groups. They were all packed. And somebody said, thank you. Just he placed it at the end of the period, end of the periodic table, and was there. As if the place for the entire family was already put. So he was successful even in that. But then they were trying to find out the factor which is going to be defining the properties of the element. Then came another person whose name was Moseley. This Moseley person, he did some experiments. And what he did was, he allowed the cathode rays or high energy cathode rays to fall on certain elements. When these cathode rays were falling on certain elements, these elements ejected out X-rays. And he found that these X-rays, the frequency of these X-rays turned out to be very sequential to their property called atomic number. Moseley allowed the high energy cathode rays to fall on the foils of the metal, and I believe I have told you, whenever the cathode rays are being suddenly stopped, they release out energy. If the cathode rays are strong enough, they have high energy enough, then the energy is released out in the form of X-rays. Now these X-rays which were being ejected out, they were having different frequencies depending on the atomic number of the substance they strike. Now this was even a more fundamental property as compared to the atomic masses. The formula that Moseley gave was that under root of the frequency of the wavelength of the X-rays is equal to A multiplied by Z minus B, where Z is the atomic number. A and B are constants. So if I make a graph of the under root of the frequency of the X-rays with respect to the atomic number, it will turn out to be a straight line. Okay? So this was Moseley's formula. Some people write it in this manner also, that nu is equal to A square upon Z minus B whole square. I don't suppose there should be any problem with that. Okay? Okay. So that was Moseley's law, and Moseley's law, this Moseley's prediction, it was converted into a law, and that said, the physical and chemical properties of the elements are periodic functions of their atomic numbers. Now this was even more dominant, even more clear as compared to the atomic masses, and we found that here, even those substances which were having very similar atomic masses, they still also could be differentiated. Not many elements were discovered after this. Now, sometimes students ask me a question. So, if the periodic properties are the functions of the atomic numbers, then was mentally such an idiot not to predict it? Now, my answer happens to be again a very simple one. At that time, atomic numbers were not discovered. Atomic numbers were discovered in 1900s only, after cathode ray experiment. Electron was not known at that time. So the only thing they knew about the atom was the atomic mass. Take important part. When you talk about this periodic table, it is not made by one scientist. The periodic table, in fact, has been made by the contribution of many scientists, inclusive of Bohr, there was Burry, there was periodic table. Now, many scientists suggested certain things. Bohr suggested that this periodic table should be divided in blocks. Some blocks. Depending on which orbital the last electron is entering. If you write the electronic configuration, then we would find that these elements, when you talk about these two elements, these two groups, the last electron goes into the s orbital. So this group was called s block. From here to here, it was called D block. From here to here, it was called and there happened to be two more groups. These were placed away from the periodic table. They were called F block. Now this is what we call as the S and the P block. They are called representative elements. The D block are called transition elements, and the F block are called inner transition in the periodic table. Whenever you see the periodic table, we have this periodic table and there are two groups separated. Now those two, apart from the others, are called the F block elements. They are called the transition elements. Be very clear, there are some general configuration of these elements. There are some general configuration of these elements. Like, when you talk about the S block elements, its general configuration is, the last shell configuration is NS1 to 2. 1 से 2 तक, 1 से 2 तक S ऑर्बिटल में 2 ही इलेक्ट्रॉन आते हैं S शेल में. तो इधर इज NS1 और NS2. ये NS1 है, ये NS2 है. ठीक है? For example, if I write the electronic configuration of potassium, इसका atomic number is 19. If I write the electronic configuration of potassium, it will turn out to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s, ns1.
So इसमें S1
इस पूरे में S1 आएगा, इस पूरे में S2 आएगा. When we talk about the configuration of p block elements, the configuration would turn out to be ns2 with np1 to 6. So this is the configuration of the p block elements. ns2 np1 to 6. So that is what we have as the p block elements. Arsenic, the atomic number turns out to be 33. The atomic number is 33. So if I talk about the atomic number 33, it will turn out to like arsenic, atomic number 33, configuration 1s2, 2s2, 2p6, 3s2, 3p6. Now we have 4s2, and after 4s2 we end up with 3d10, and then we have 4p3. Okay, so if I leave apart 3d, which is n minus 1, I get ns2 np3. So this is the typical feature of the p block elements. Then we talk about the d block elements. Now d block elements have a peculiar characteristic that they have a configuration of ns0 to 2, ns0 to 2, n minus 1, d 1 to 10. So this is the configuration of the transition elements. That is how we find it.